Welcome to this video on single-phase and three-phase electrical systems. We will cover key concepts like power, circuits, protection, quality, and analytics. This video covers 20 topics, starting with the fundamentals of AC systems and progressing through single and three-phase architectures, power calculations, transformers, motors, and protection devices. Alternating current, or AC, reverses direction periodically, enabling efficient power transmission. We examine frequency, sinusoidal voltage, RMS values, impedance, power factor, and worldwide AC standards. Single-phase systems use two conductors, line and neutral, for residential and light commercial use. The voltage levels vary by region, with standard voltages like 230 volts and 120 V. Single-phase applications are generally limited to smaller loads and motors, up to around 2.2 kilowatts. Three-phase systems use three conductors, 120 degrees apart, for constant power delivery. Common configurations include star and delta, affecting voltage levels and the need for a neutral conductor. Three-phase offers advantages over single-phase for larger applications. Phasor analysis is key to AC engineering. We review fundamental principles such as Ohm's law and KVL, KCL in AC, power equations, star-delta conversions, symmetrical components, and the per-unit system. Power is comprised of real, reactive, and apparent power, represented by the power triangle. Understanding this triangle is essential for power factor correction and power measurement, particularly when comparing single-phase and three-phase power delivery. We explore single-phase and three-phase transformer design, including core construction and efficiency. Key aspects include tap changers for voltage regulation, transformer losses, and the vector groups defined by IEC 60076. Differential protection methods ensure transformer safety. Single-phase motors, such as split-phase and capacitor start types, are typically for fractional horsepower applications. Three-phase motors, like the squirrel cage type, are highly efficient, ranging up to 25 megawatts plus, utilizing various starting methods such as DOL or VSDs. Protection devices must be selective, sensitive, fast, and reliable in both single and three-phase systems. Devices include MCBs and MCCBs, RCDs, overcurrent relays, differential relays, and earth fault protection. These are critical for system safety and coordination. Power factor correction is an economic and technical necessity. Correction reduces apparent power and avoids utility charges. This is achieved using capacitor banks, detuning reactors, and synchronous compensators. Limits and standards govern PF and harmonic current management. Power quality encompasses various parameters and disturbances. These include voltage sags, swells, total harmonic distortion, flicker, and voltage unbalance. Standards like IEEE 519 and IEC 61000 series define limits and mitigation strategies for these disturbances. Earthing systems are classified by IEC 60364 as TN, TT, or IT, each defining the connection of the neutral and protective earth conductors. Proper neutral conductor sizing is crucial, especially in three-phase systems with non-linear loads. The power distribution hierarchy ranges from high-voltage transmission down to low-voltage end use. This system facilitates the transformation of electricity through substations to meet diverse single-phase and three-phase needs. Distribution networks include radial, ring main, and mesh/grid systems, offering varying levels of reliability and complexity. Single-phase loads, common in residential areas, are often supplied by taps from three-phase mains, requiring careful load balancing. Cable sizing must follow the IEC 603645552 methodology, considering current rating, voltage drop, and short circuit rating. Correction factors for ambient temperature, grouping, and thermal insulation must be applied, and voltage drop must be checked to meet IEC limits. Variable speed drives, or VSDs, utilize a rectifier, DC bus, and inverter architecture. Single-phase input VSDs are used for smaller loads, while three-phase VSDs are standard for industrial applications, offering significant energy savings and various protection features. Renewable energy integration involves residential and commercial solar PV, wind turbines, and battery energy storage systems. All installations require anti-islanding protection and compliance with various grid codes and standards, such as IEC 61727 and IEEE 1547. Electrical safety is governed by standards like IEC 60364, NFPA 70, and BS 7671. Arc flash and lockout/tagout procedures are crucial for worker safety, and equipment must meet specified IP and IK ratings for protection against ingress and impact. Fault analysis is dominated by the common single-phase earth fault. Three-phase faults, though rare, determine circuit breaker capacity. Protection coordination uses grading methods to ensure selective fault clearance, often modeled with specialized software. We reviewed practical design examples, including single-phase circuit sizing for a 3 kilowatt shower and a three-phase motor circuit for a 15 kilowatts motor. Calculations covered current, cable selection, and voltage drop checks. We also examined power factor correction and short-circuit current calculation. In summary, master the fundamentals of single-phase versus three-phase power and the power triangle. Prioritize selective and fast protection, ensure compliance with international standards, and always consider derating factors for cable sizing and quality limits for harmonics. Thank you for viewing this video on single-phase and three-phase electrical systems. For more content on electrical engineering and power systems, please consider subscribing.